students, in this lecture I am going to start a new topic students. Write down Fourier series. Or students, Fourier series. Fourier series. Now, the Fourier series have so many applications in engineering field, students. So many applications. We can see some example, students. Signals and systems. Signals and systems. Signals and systems are wave equations. Wave equations or image processing. Okay, students, signals and processing. There is a signal, students. Signals like this. Signals. Wave equation. Wave equation, we know, students. Wave equation. Now, if you observe these two examples, there is a common term, students. There is a common term. The common term is periodic. Or students, periodic. Common term is periodic. Now, whenever you observe the nature of the periodic, for such functions, we can find or we can apply the concept of Fourier series. For students, we can apply the concept of Fourier series. Now, let us see what is the definition of periodic function. Right? Periodic function. If f of x plus capital T, that is equal to f of x, students. For students, f of x plus capital T, that is equal to f of x. Now, what is T here, students? T is called here period. T is called period. Now, if f of x plus t is equal to f of x, then f of x is said to be periodic function with period. What is period, students here? Period capital T. With period capital T. With certain after period, the same function will come. Such functions are called periodic function. We have so many examples, students. We can give an example, sin x. Or students, sin x. Sin x is periodic function with period. Come on, tell me, students. 2 pi. Similarly, cos x is periodic function with period 2 pi. Tan x is periodic function with period. Is it 2 pi? No, it is pi. Tan x is periodic function with period pi. Now, I am going to discuss the definition of Euler's formulae and Fourier series. Let us see, students. Write down, students. Euler's formulae. In the Euler's formula, we have the definition of Fourier series, students. Fourier series, right? The Fourier series of a function f of x. The Fourier series of a function f of x in the interval alpha less than x less than alpha plus 2 pi. But students, alpha less than x less than alpha plus 2 pi is given by the Fourier series of a function f of x in the interval alpha less than x less than alpha plus 2 pi is given by. Now he defined the Fourier series, students. Here f of x is equal to a naught by 2 plus sigma an cos nx, where n is equal to 1 to infinity, plus sigma n is equal to 1 to infinity bn sin nx. bn sin nx. This is Fourier series, students. This is Fourier series. Once again, students, what is Fourier series? f of x is equal to a naught by 2 plus sigma n is equal to 1 to infinity an cos nx plus sigma n is equal to 1 to infinity bn sin nx. Where n starts from here, students, n is equal to 1 to infinity. 1 to infinity. Now, in this Fourier series, what we are going to find, students? We are finding the values of, come on, tell me here. Yes, exactly. A naught, an and bn. Now we need to define what is a naught, an and bn. So right now, students, where a naught that is equal to 1 by pi integral alpha to alpha plus 2 pi f of x dx. What is an, students? 1 by pi integral alpha to alpha plus 2 pi. Because our interval is, students, alpha to alpha plus 2 pi. That's why here the lower limit is alpha, upper limit is alpha plus 2 pi. f of x. What is an here, student? An coefficient? Cos nx. So you write cos nx dx. And bn, students, 1 by pi integral alpha to alpha plus 2 pi. What is bn coefficient, students? Sin nx. So f of x is given function, students. f of x sin nx dx. Now if you find a naught, an, bn values and substitute here, then you got the Fourier series of the given function, students. The Fourier series of the given function. Now here a naught, an and bn are called here. A naught, an, bn are called, students, Euler's formulae. Or students, Euler's formulae. This is about Euler's formula, students. Once again, students, what is Euler's formula? The Fourier series of a function f of x in the interval 0 less than x less than alpha plus 2 pi is given by students. This is the Fourier series. f of x is equal to a naught by 2 plus sigma n is equal to 1 to infinity an cos nx plus sigma n is equal to 1 to infinity bn sin nx, where a naught is equal to 1 by pi integral alpha to alpha plus 2 pi f of x dx. an value, students, 1 by pi integral alpha to alpha plus 2 pi f of x cos nx dx. And bn value, students, 1 by pi integral alpha to alpha plus 2 pi f of x sin nx dx. Here a naught, an, bn are called Euler's formula. Now, in this entire chapter, or say half of the chapter, or what is the basic intervals are here. Basic intervals are here 0 to 2 pi or minus pi to pi, students. Or students, 0 to 2 pi and minus pi to pi. These two intervals are almost all 50% of the chapter we are using, students, and further also. Right? This is very, very important, students. Now, in basic definition, we have alpha less than x less than alpha plus 2 pi. Instead of that, you put 0 to 2 pi and minus pi to pi. Okay, student. Result or note. Say this result 1. The Fourier series, similar mentions. The Fourier series of f of x in the interval say here, students, 0 less than x less than 2 pi, x less than 2 pi is what is f of x, students? Here f of x is equal to a naught by 2. This time, students, sigma n is equal to 1 to infinity a n cos nx plus sigma n is equal to 1 to infinity b n sin nx. Here a naught value limits are changed, students. A naught is equal to 1 by pi integral. Previously we have alpha plus 2 pi, students. Now here 0 to 2 pi. So you just write 0 to 2 pi. 0 to 2 pi. F of x dx. Now what is a n value, students? 1 by pi integral 0 to 2 pi f of x. F of x, how much, students? Cos nx dx. And what is bn value, students? Bn value 1 by pi integral 0 to 2 pi f of x sin nx dx. Sin nx dx. Now I want to find the Fourier series in the interval minus pi less than x less than pi, students. Right now, students, result 2. Result 2. Right. The Fourier series of f of x, the Fourier series of f of x in the interval previously we have 0 less than x less than 2 pi, students. Now the another interval is very good, minus pi less than x less than pi is now what is f of x, students? Here f of x is equal to, same, students, a naught by 2 plus sigma n is equal to 1 to infinity a n cos nx plus sigma n is equal to 1 to infinity b n sin nx. Bn sin nx. Now what is a naught value, students? Here 1 by pi integral. The limits are changed, students. What is the limit here? Minus pi to pi. So you write here minus pi to pi f of x dx. F of x dx. What is a n value, students? 1 by pi integral minus pi to pi f of x. What is coefficient here, students? Here cos nx dx. Now bn value 1 by pi integral minus pi to pi f of x, here sin nx dx. Sin nx dx. This is the Fourier series, students, for minus pi less than x less than pi. Minus pi less than x less than pi. Now we need some basic definition, students, to easily solve the problems further. Right? Let us see the basic definition, students. Basic definition. So what is even function, students? Even function. Even function. F of x is said to be even if f of minus x is equal to f of x, students. Or students, f of x is said to be even if f of minus x is equal to f of x. F of minus x is equal to f of x. For example, if I am taking here f of x is equal to x square, students, x square. So f of minus x, students, that means minus x whole square. That is equal to get here again x square. So x square is even function, students. Even function. We can give another example, students. F of x is equal to cos x. Cos x. We know cos minus x is equal to cos x. Cos x is also a even function. Therefore, what is the conclusion here? X square, x power 4, x power 6, x power 8, and so on. And cos x also even functions. Are even functions. Now, odd function. Or students, odd function. F of x is said to be odd if f of minus x is equal to minus f of x, students. For students, minus f of x. Now, we can give so many examples, students, here. So many examples. What are the examples here? F of x is equal to x, students. Now here, f of minus x, that is equal to minus x. This is minus f of x. So, f of x is odd function. Similarly, generally we know f of x is equal to sin x. Sin x is odd function. Sin x is odd function. Now here we have some basic definition, students, here. Basic concepts here. The concept is even into even, students. Even into even. We remember this, students. Even into even is even. Even into odd. Even into odd is odd, students. Odd into even. Odd. Odd into odd. Even. This is very, very important, students. Because whenever we solve the problems by applying this, we can easily find the solution, students. Otherwise, it is very difficult to evaluate the integrations. If you are evaluating, there may be chance to done small mistakes. If I am applying these concepts, not only all the problems, students, not only all the problems, whenever you observe the intervals like minus pi less than x less than pi, in such cases we can apply this concept, students, even into odd. So, even into even, students, even into even. We can give students say even into even, x square into cos x, students. Again we get here even. Even into odd, students, even. Say x square I am taking here into sin x. We get here odd, students. Odd into even, just over, students, sin x into x square. We get odd. Odd into odd, students, odd into odd, x into sin x. X into sin x. We get here even function, students. This is very, very important, students, to evaluate the integration easily. Let us see some more basic definitions, students. Write down, students, some more basic formula. We know, everybody knows, students, this one, integral minus a to a f of x dx. F of x dx. Now, this can be written as, students, 2 into integral 0 to a f of x dx. F of x dx. When we can write 2 into, students, 2 into integral 0 to a. Good. F of x is even. For students, f of x is even. And 0, f of x is odd. So, value is 0, students, when f of x is odd. Last but not least, students, this is very, very important formula, because we are applying this formula entire Fourier series, students. So, listen carefully and practice number of times, students. Right. The formula is here. Integral of uv, students. Integral of uv. Generally, everybody knows, students. What is integral of uv? U integral v minus integral of derivative of u integral v. If you are integrating with respect to x, write integral with respect to x. Y, you can write y. This is basic integration formula, students, by parts formula. Now, these are the modifying, students. Generalize integration by parts. For students, generalization of integration by parts formula. So, same formula, students, integral of uv, that is equal to, same, u, integral of v1 means, students, integral of v. v1 means integral of v. Suffix stands for integration, students. Suffix stands for integration. Minus. Later we have, students, du. Du means derivative of u. Derivative of, say, this is u dash. And then integral v here, and again integration. So, I am writing here v2. See, students, next term is plus. Now this time we get a u double dash, students. U double dash. And then in v2 plus write v3. Next step, students, next term, write minus, students. because you get plus and minus alternatively. So u triple dash, come on, tell me students here, v4 plus and so on, plus and so on. This is generalization of integration part by parts number, students. Once again, students, u v1 suffix means integration minus u dash, students. You find derivative of this u, you get u dash. v2 students, already you integrate here. So once again you integrate this, you get v2. Okay, students. That means you take once again, you integrate once and twice. Don't do that, students. It is very difficult to you. So how can you get u double dash, students? Yes, exactly. U dash here. Again you differentiate. You got u double dash. v3. Here already we have v2. Again you integrate this. You get v3. Similarly, rest of the terms. So this is about Fourier series basic definition and some basic formulas which are very, very important in the Fourier series, students. Hope you understand. Thank you. Thank you for watching this video. Jai Hind.